Hey everyone, and welcome to this exam prep explainer. Today, we're going to break down exactly what you need to know to absolutely master Section 16.1 of the Nutanix NCP-MCI 7.5 Certification Blueprint. If you're an infrastructure admin gearing up for this exam, you probably already know that understanding the nuances of baseline AOS 7.5, AHV 11.0, and Prism Central 7.5 is completely non-negotiable. Cluster expansion is actually a really frequent source of those tricky scenario-based questions on the exam, and there's a good reason for that. It uniquely bridges networking prerequisites, hardware compatibility rules, and some pretty complex storage resiliency concepts. So we aren't just going to look at which buttons to click in the UI, we're going to deeply explore the underlying architectural rules that dictate how a Nutanix environment scales safely and efficiently.
Okay, let's take a quick look at our roadmap for today. We'll start with why expansion matters, walk through the actual UI process, highlight the exam traps that always catch people off guard, and finish up with the strict facts you absolutely need to memorize.
Section 1. Why expansion matters.
To properly answer the scenario-based questions you're going to face, we first have to wrap our heads around the core architectural philosophy of how and why we expand a cluster. Because let's be real, it's never just about blindly adding more compute or storage. A Nutanix cluster is this living, highly sensitive distributed system. The ultimate goal of cluster expansion is scaling out your resources without a single second of downtime, all while ensuring new nodes seamlessly sync up to run the exact same versions of AOS. That's the Acropolis operating system, and AHV, the Acropolis hypervisor. When you bring in a new node, the cluster actually uses its existing AOS baseline to image that node. The expansion process automatically checks the AOS version on the running cluster against the new hardware and performs any necessary upgrades or downgrades. Think of it as a strict leveling event. The exam will definitely test your knowledge on this. New nodes never run disparate versions of AOS or AHV. The expand cluster process enforces absolute 100% homogeneity before a node is ever allowed to touch production workloads. That's how it maintains perfect cluster consistency.
Moving on to Section 2. Expand cluster walkthrough.
Let's talk about how this actually looks. In Prism Element or Prism Central PC.7.5, you initiate the scaling process by navigating to Hardware, then Clusters, and clicking the Expand Cluster button. Behind the scenes, the system immediately starts hunting across your subnet for unassigned prepared nodes. It's specifically looking for nodes that either have the hypervisor and a CVM, a controller VM already installed, or nodes sitting in a factory-prepared state. Once it finds them, you just select your desired hosts. But right here, you have a critical architectural choice to make. You can either expand immediately, or you can choose the Prepare Now and Expand Later option. As an exam candidate, you need to know exactly why an admin would choose the latter. You'd use Prepare Now and Expand Later to get the lengthy, CPU-intensive imaging process out of the way during normal business hours. Then, you can delay the actual cluster join, which immediately kicks off a massive storage rebalancing operation across your network until a strict nighttime maintenance window. It's a lifesaver for performance.
Let's look at a concrete example. Imagine you're unboxing a brand new factory-prepared node running Discovery OS. Now, what actually is Discovery OS? Basically, it's a super lightweight temporary operating system installed at the factory. It's designed to do just one thing: wake up and broadcast its presence to an existing Nutanix cluster over the network. Because a node running Discovery OS isn't pre-imaged with a functioning hypervisor or production-ready AOS installation, it has to go through a full imaging phase first. And the beauty of this is that the Expand Cluster UI is smart enough to handle all that heavy lifting directly. It intercepts that network broadcast, takes over the node, completely strips away Discovery OS, and seamlessly images it with the exact AHV hypervisor and AOS version required to perfectly match your running cluster. And it does all of this before officially joining it to the storage ring.
For example B, let's dive into strict architectural placement, because respecting block and rack awareness constraints during an expansion is an absolute must. Walk through a quick mental exercise with me here. Imagine a fully loaded server rack. Suddenly, a top-of-rack switch completely dies. Or maybe a specific power distribution unit fails, instantly killing power to an entire 4-node block, which, if you aren't familiar, is a physical 2U rack-mountable enclosure that shares backplanes and power supplies. Thanks to block fault tolerance, the Nutanix cluster easily survives this kind of catastrophic hardware loss. How? Because the system deliberately placed redundant copies of your data and metadata on nodes that reside in completely different physical blocks. So when you're expanding your cluster, you aren't just throwing more CPU cycles at it. You're actively extending this physical fault domain. By distributing your new nodes across multiple blocks, you ensure that if an entire enclosure goes dark, your cluster stays fully online and operational without missing a beat.
To make that incredible block fault tolerance possible, Nutanix relies heavily on something called a metadata ring. Metadata is basically the crucial map of where every single piece of user data lives in the cluster. To protect this map, metadata forms a ring structure across those physical hardware boundaries. In order to maintain block awareness and safe metadata distribution, especially in specific, high-availability setups, you absolutely must have enough physical blocks to form a strict quorum. A quorum is what prevents split-brain scenarios, where half the cluster thinks it's in charge and the other half disagrees. This is exactly why, if you're aiming for a redundancy factor of 3, which lets you withstand 2 simultaneous node or drive failures in entirely different blocks, you need a minimum of 5 physical blocks. The metadata quorum algorithm fundamentally requires it to safely distribute the copies.
Looking at the numbers behind this fault tolerance reveals a strict architectural rule that you really need to master. Replication factor, or RF, dictates exactly how many copies of your data exist on the network at any given time. Notice that metadata is always more heavily protected than standard user data. For a cluster to survive 2 simultaneous node or disk failures, often noted on the exam as a 2N/2D cluster fault tolerance, the underlying user data requires a replication factor of 3. However, the metadata requires a replication factor of 5. This strict requirement is exactly why you have to carefully plan your cluster expansions. You aren't just adding random storage capacity, you have to ensure you are adding enough distinct physical blocks to satisfy those massive metadata ring requirements.
Section 3. Exam traps and edge cases. Knowing the standard happy path is great, but knowing exactly where the process breaks is what will actually earn you your certification. Picture this scenario. You rack a new node, cable it up perfectly, jump into the expand cluster window, hit discover, and nothing. It completely fails to find the host. Why did this happen? The crucial takeaway here is that automatic discovery relies entirely on IPv6 multicast packets. Why IPv6 multicast? Well, it allows brand new unconfigured nodes to dynamically discover each other using link local addresses, all without requiring you to have a pre-configured DHCP server sitting on your management network. It makes the unboxing experience completely seamless. But, and this is a big but, this architecture fundamentally breaks if your networking team applies restrictive switch port security that drops multicast traffic, or if they've completely disabled IPv6 routing on that VLAN. The discovery process will just silently fail. If enabling IPv6 simply isn't an option in your highly secured environment, your only workaround is to manually punch the IPv4 addresses of the new nodes into Prism to force that discovery handshake. Okay, here's a massive exam trap regarding bare metal nodes. Expand Cluster and Foundation are 2 very different tools. Foundation is a bare metal imaging tool. Expand Cluster is a cluster scaling tool. Expand Cluster expects a handshake from the new node via Discovery OS or pre-installed software. If you buy hardware from a vendor without an OEM agreement, it might arrive completely blank. I mean, no software, not even Discovery OS. Because there is no software to handshake with, the Expand Cluster UI is entirely blind to it and literally cannot perform direct bare metal imaging. In this specific scenario, you have to use the Foundation tool first to forcefully image the bare metal node, and only then can you use Expand Cluster to bring it into the fold. Don't let them trick you on that one. Pay really close attention to node mixing rules. Cluster expansion has to follow a strict order of hardware progression. Why? Because the Nutanix cluster operates at the speed of its slowest node for a lot of distributed storage tasks. Adding slower, older generation storage nodes to a high-performance cluster would severely drag down the overall storage fabric performance. So you can add a newer, faster tier, like hybrid NVMe plus HDD nodes, to an older cluster of hybrid SSD plus HDD nodes. But you absolutely cannot do the reverse. Adding older SSD technology to an NVMe cluster is unsupported. Furthermore, when you are mixing node types, the minimum number of each node type added must equal your cluster's replication factor. If you are running RF3, you can't just add 1 new node type, you must add 3. This builds into even stricter requirements when we introduce erasure coding, or EC. EC increases your usable storage capacity, which is great, but it dramatically impacts your expansion rules. Think of erasure coding kind of like RAID, but distributed across your entire network. It creates these complex data stripes and parity pieces. To ensure that the physical loss of a single block doesn't destroy both a piece of the data stripe and its parity calculation at the exact same time, EC demands a much wider physical distribution.
That is exactly why, if you use erasure coding on a storage container, you need a minimum of 4 blocks for replication factor 2 or 6 blocks for replication factor 3. If you don't meet these strict block minimums during expansion, your block awareness is entirely lost when EC is enabled.
Section 4, Facts to Memorize.
Treat these final points as the 4 golden rules you must memorize before exam day. Number 1, IPv6 multicast is absolutely mandatory for auto-discovery. If it's blocked, you're manually using IPv4. Number 2, mixed node minimums must equal your cluster's replication factor to maintain resilient distribution. Number 3, the expand cluster process does not support compute-only node preparation. Those require an entirely different workflow. And number 4, CVM memory leveling. If the controller VM memory on a newly added node is less than the current nodes, let's say it defaults to 24 gigabytes, while your current cluster is already running 32 gigabyte CVMs, Prism will automatically bump the new CVM up to 32 gigabytes to ensure perfectly balanced storage performance across the entire environment.
As you sit for the NCP-MCI 7.5, whenever you face a cluster expansion question, I want you to ask yourself, am I actually maintaining my fault domain boundaries? If you truly understand the metadata RIN, block awareness, and the strict networking prerequisites we covered today, you won't just pass the exam, you'll be architecting incredibly resilient environments in the real world. Good luck and happy studying.